Instead of having to work through all the nasty math, we can use our hypothesis test method instead to try to see if it's in your benefit to switching doors. But in order to use statistics, we have to take a sample from the population. So we'll simulate what would happen if we repeatedly play this game over and over and over again. And this website will let you simulate picking a door. Let's just start off by picking one of these doors at random. So I'll pick door number 3. And then what the simulation is going to do is there's 2 doors left. At least one of them has a goat behind it. Since Monty Hall knows which one has the goat, he'll go ahead and reveal door number 2. Now the question is, do we want to switch? And what we want to try to learn about is the proportion of all games we would win by switching. So we always want to switch. Since I picked door number 3, I'll go ahead and switch my choice to door number 1. And in this case, we happen to win the car because it was behind door number 1 after all. And down here, it has the total number of times people have played this on this website. 161 times people switched, 74 times people didn't switch. And we're only interested in the number of times that people switch. There was 161 games played where somebody ended up switching doors. They won 109 times for a sample proportion of about 67.7%. So we'll use this as our sample data, our evidence, to try to see if to change our mind away from the null hypothesis into the alternative hypothesis. We have a null hypothesis, and since there are 2 doors left after Monty Hall opens one of the doors, we'll say our chances of winning if we switch is going to be equal to about 50%, or the population proportion of games that we win the car should be equal to 50%. And our evidence that we collected from the simulation is they ended up winning 109 times out of the 161 games they played for a sample proportion of 0.667. And the question we want to try to answer is, why is our sample proportion different from the value in the null hypothesis? Why did we get a sample proportion of about 68% if we believe the population proportion really is 50%? And there's going to be 3 reasonable explanations. The first one is just that the population proportion is not equal to what we believe it is. Essentially, that our null hypothesis is wrong. If you win 2/3 of the time or 70% of the time, it would make sense that our sample proportion is different from the value in the null hypothesis. So that's our first option. It's just that our default belief is wrong. Another explanation is that our null hypothesis is correct, just what we saw happen due to random chance. And so the second explanation is saying that the null hypothesis is true. And the idea is, even if you win 50% of the time, if you play a sample of 161 games, you won't win exactly 50% of them. In fact, if you play 161 games and you win half the time overall, you can't win exactly 50% in our sample. And the idea, if you think about it in a little more simpler sense, is if you flip a fair coin 100 times, fair means you have 50% chance of heads, 50% chance of tails. It doesn't necessarily mean that you'll always get 50 out of 100 of your flips to end up on heads. Since we're taking things randomly, there's always this random influence behind it, and you don't always get exactly what you expect. So one explanation is that the null hypothesis is true, and our sample proportion just doesn't line up with it due to random chance, this taking a random sample part. And the last explanation is that we took a bias sample. If the null hypothesis is true and you take a bias sample, p hat won't be equal to 0.5. Because when you have bias samples, they always end up being different than the population parameter. But since we took a random sample, we didn't know which door had the car behind it. So we were just picking our initial door at random and then switching. You can cross this option off the list. So that leaves us down to one of 2 explanations. The population proportion is different than what we believe versus the population proportion is what we believe. Just the difference that we saw was due to random chance. So how do we go about figuring out which of these 2 options we want to go with? So what we need to do is figure out how often our sample statistic would occur just by random chance when the null hypothesis is actually true. So what are the chances if we play this game 161 times, we just happen to win 109 or more of them? So what we want to find is, what is the probability of getting a sample statistic greater than our observed statistic. And we're looking at greater because that was the sign in our alternative hypothesis. We're only really interested in switching if it increases our chances of winning, if it makes the proportion of games we win greater than 50%, given or assuming the population proportion is what the null hypothesis says it is. So we'll assume the null hypothesis is true, and then find the probability of getting our sample statistic just by random chance. So the first thing we can do then is just let's simulate it, kind of like what we did for our sampling distribution. If we essentially flip a coin 161 times, what are the chances we would happen to get 109 or more of them to be heads? What are the chances we would win 67.7% of the games played just due to random chance? What this will let us do is if we click generate one sample, it'll flip a coin 161 times. In this case, they happen to get 78 of them to be heads for a sample proportion of about 48%. And it'll just place a little dot down here at 48%. And if we do it again, flip the coin 161 more times. This time 64 of them ended up being heads for a sample proportion around 40%. So it places a dot down here right at 40%. If we do it again and again and again, every time it's going to generate a new sample of 161 coin flips where your chances of getting a heads is at 50%, count how many of them end up actually being heads, and record a sample proportion. And to simulate what would happen if we did this over and over and over again, to figure out what are the chances you guys would just end up getting really lucky and winning the car 67.7% of the time out of 161 times we played the game, let's generate not one sample of 161 or 10 samples of 161. Let's generate thousands of them. So if we click this generate 1,000 samples button a few times, we end up now with 5,000 samples. So essentially we have 5,000 dots down here, and each one of those dots represents a single sample of 161 games played and the proportion of them where they ended up winning. And we want to know how often did they win 67.7% of those games. And if we look down here, it appears of these 5,000 simulations, it never happened more than 68% of the time. In fact, it rarely happened more than 60% of the time. What we can do then, if we want to figure out the actual probability, is we can click on this right tail because we want the number of dots above our sample proportion of 67.7%. We can click down here, change this to 0.677, our sample proportion, and we can see that 0% of the time we got a sample proportion as big or bigger than the ones that we observed when the null hypothesis is true. Basically, it's very, very unlikely to get our sample when our null hypothesis, our default belief, is correct. So one way we found this probability is just by simulating it. Essentially, if you have a 50% chance of winning, it's down to a coin flip. We flipped 161 coins 5,000 times and saw how often we would win 109 or more of those coin flips. Another way, a more statistical way of going about it, is we can just build a probability model. And how do we go about doing that? Well, we can use what we learned in chapters 13 and 14 and use the central limit theorem to see how often our sample proportion would occur when the null hypothesis is true. If you look back at those simulated sample proportions, they ended up being bell-shaped. They ended up being normal. That means it makes sense to use the central limit theorem. And what the central limit theorem said, as long as we meet a couple of conditions, one, we need our cases to be independent. We need each one of those games we played to not influence the result of the next one. We can check that by saying, did we get a random sample? And as long as we don't know where the car is, as long as we're not cheating, we can assume all those games played are a random sample of all possible games that could be played. And the next one is we want to make sure our sample size is less than 10% of the population. Well, in the Monty Hall case, there isn't a population size. It's theoretically infinite. We could play this game until the end of time. If you have an infinite population, then our sample size of 161 is less than 10% of infinity. So we also can check that one off. So we have independent cases, and the next one we need to check is, do we have a large enough sample size to use a normal distribution? How do we go about checking for a sufficient sample size when we're working with a proportion? First thing we want is to make sure that we have at least 10 successes, or we can expect at least 10 successes. We'll take our sample size, multiply it by what the null hypothesis says the population proportion should be. As long as that's greater than or equal to 10, we'll have at least 10 expected successes. In our case, we have a sample size of 161. Multiply that by 0.5, and you get 80.5, which is greater than 10. And then we'll do the same thing, but now for our number of failures. If we expect to win half the time, we should expect to lose half the time. So it's still 161 times 1 minus 0.5, and that'll also give us 80.5. Then our sample size is large enough, so that way our sample proportion will follow a normal model. And the entire time we're doing this hypothesis test, we'll assume our null hypothesis is true. That means that p hat should follow a normal distribution, centered at whatever the population proportion is. And again, we're assuming the null hypothesis is true, so that means we should know what the population proportion is. And then our standard error formula will be p0 times 1 minus p0 over our sample size. And if you pay attention, this is a little bit different than our standard error formula when we're working with a confidence interval. In a confidence interval, there is no assumed value for the null hypothesis. So there is no p0 for a confidence interval, so our next best guess would just be to plug in p hat. For a hypothesis test, we have a better guess than our sample data. We have what the null hypothesis says, so we'll plug that in here. And you want to pay a little close attention and know that there's a difference in the standard error formula between a confidence interval and a hypothesis test. They're slightly different. One uses the null hypothesis value, the other one uses your sample proportion. In our case, p0 was 1/2, and so we plug it in to our central limit theorem formula, and then we'd end up with a normal model we can use to find these sample proportions and how often our sample proportion would occur. If we plug in our values into our central limit theorem formula for p hat, we end up with the mean of this normal model to be 0.5, and the standard error of the normal model to be about 4%. Well, what we want to do is draw where our sample proportion, p hat, is equal to 0.677. We want to see where it falls. And you want to remember the normal distribution. These tail ends fall about 3 standard deviations away. So if we round off to 4%, tail end areas kind of fall off at about 62%, or 0.62. That means our sample proportion of 0.677 would fall somewhere down here. And then what we want to do is we want the area above our sample proportion, because our alternative hypothesis way back at the beginning was that p is greater than 0.5. So what are the chances we get a sample proportion as big or bigger than the one that we found? So we'll shade this area above our sample proportion. And all we need to do is figure out what this tail area is. Well, we're looking for an area. We're given a number. That means we want to use normal CDF. We start shading at 0.667. And we theoretically stop shading at some large positive number. And then we need to enter in its mean and its standard deviation. We can pull up our calculator. We can go to sec and vars. We want normal CDF, so we'll click on option 2. 0.677 for our sample proportion, because that's where we start shading. We stop shading at some large positive number. We have a mean of 0.5 and a standard error of 0.039. And if we enter that in, we end up with this probability of being about 0.0000028. So this area is going to be 0.00028. Something that would happen about 3 in 100,000 samples. And if we believe our null hypothesis is true, then the chances of winning 67.7% or more of your games just through a random chance happens about 0.003% of the time. So not great chances of getting what we observed by random chance alone.